There is one law of physics that knows the difference between yesterday and tomorrow. Only one. Drop a glass on the floor and it shatters. You have never, in your entire life, seen the shards leap back up and reassemble. You never will. Not because the laws of motion forbid it. They don't. The atoms could, in principle, conspire to send every fragment back into place. The reason it never happens is statistical. There are vastly more ways for the glass to be broken than whole, and the universe, given any choice, drifts toward the more numerous option, every time. Without exception. This is the second law of thermodynamics, and it is the closest thing physics has to a death sentence written into the fabric of reality. Everything you have ever loved is a temporary arrangement of atoms drifting toward a more probable state. Your body, your memories, the sun above you, the galaxy holding it in place. All of it is a local pocket of low entropy borrowing time against an inevitable bill. The universe is not eternal. It is running down. And tonight, while this voice reaches you and slow cosmic images drift across the screen, we are going to walk through what the running down actually looks like, all the way to the end. Past the last star, past the last black hole, past the last particle of light, to the place where nothing happens anymore because nothing is left to happen to. And then we are going to ask the question almost no one asks. The question Roger Penrose was willing to ask in public and was nearly laughed out of the room for. What happens after that? Because the answer he gave does not just rewrite the end of the universe. It quietly suggests that the beginning was not the beginning either. Stay with this. The last act of the cosmos is stranger than the death it walks into. To see why, you need to understand how astonishingly early we are. Not late. Early. The universe is roughly 13.8 billion years old. That number feels enormous to us because we measure our lives in decades. But hold it in your mind for a moment, because the astrophysicists Fred Adams and Greg Laughlin did exactly that, and what they found in their 1997 paper on the long-term fate of the cosmos changed how serious people talk about time. They divided the entire future of the universe into eras, and the era we live in, the one where stars actually shine and planets actually form and chemistry actually does interesting things, they called the stelliferous era. The starry era. It sounds grand. It is not. On the timescale Adams and Laughlin drew, our entire era is a flicker. A spark at the start of a fuse that burns for 100 trillion years and then keeps burning dimmer and dimmer, for a number of years so large that human notation can barely write it down. Think of it this way. Imagine the full lifespan of the universe stretched along a single line in front of you, from the Big Bang to the absolute end. If you compress that line so the entire stelliferous era, all 100 trillion years of stars and planets and possible life, fits inside the first inch, then the rest of the line extends past the horizon, past the next room, past the next country. The cosmic time during which the universe actually looks like anything you would recognize is an inch. The rest is darkness. The stars you see when you walk outside at night are not the normal state of the cosmos. They are the brief exception. We are not the children of the universe. We are the spark before it. And the spark is already dimming. The Milky Way is currently forming stars at about 1 solar mass per year. 4 billion years ago that rate was roughly 10 times higher. The hydrogen that fuels stars is being burned, locked away in dead remnants, and not replenished. Every red dwarf that flickers on tonight, and red dwarfs will outlive every other kind of star, is one less hydrogen budget for the rest of cosmic history. Adams and Laughlin estimated that the last star capable of fusion will ignite somewhere around 100 trillion years from now. After that, no new fire. Only the slow cooling of what remains. What remains is what cosmologists call the degenerate era, and the name is exact. The matter left behind has collapsed into its densest possible forms. White dwarfs, the smoldering carbon-oxygen cores of stars like our sun, packed so tightly that a teaspoon of their material would weigh as much as an elephant. Neutron stars, even denser, a teaspoon weighing as much as Mount Everest. Every atom crushed until the electrons have been forced into the protons and only neutrons remain. And black holes, the densest objects of all, where the crushing has gone so far that geometry itself folds inward and light cannot climb back out. By the time the degenerate era is in full swing, perhaps 10 to the 15th years after the Big Bang, those are the only objects left. A scattered population of corpses drifting through space that has cooled to within a fraction of a degree of absolute zero. And here is where the story gets worse than you expected. The corpses are not stable. Most physicists working in grand unified theories of particle physics suspect that the proton itself, the seemingly indestructible building block of every atom in your body, eventually decays. The current experimental lower limit on the proton's lifetime, set by detectors like Super Kamiokande deep beneath a mountain in Japan, is more than 10 to the 34th years. That is not a measurement of how long protons live. That is a measurement of how long we have failed to catch one dying. The actual lifetime, if proton decay is real, could be 10 to the 34th or 10 to the 40th or longer. Pick a number. The point is that in deep cosmic time, even the protons inside your bones are temporary. Imagine a white dwarf, a dead star no longer fusing, simply radiating away the last of its stored heat into the void. It cools for 1 trillion years, then a quadrillion years, then a quintillion years. Now imagine that its very atoms are coming apart from the inside, one proton at a time. The star, already cold, is also dissolving. Over 10 to the 40th years it slowly evaporates, not into light, but into nothing recognizable. The same fate awaits every neutron star, every planet, the frozen remnants of every world that ever held an ocean. By the end of the degenerate era, ordinary matter as you and I know it is gone. Not transformed. Gone. The atoms that built you have unraveled into stray photons and electrons drifting through cold space. And then there are only the black holes. This is where the universe enters what Adams and Laughlin called the black hole era, and where the timescales begin to break the mind. Black holes are the last titans. They have been growing this whole time, swallowing the leftover matter that fell into them, merging with each other, becoming the only structures in the cosmos that still have any density worth speaking of. By 10 to the 40th years, the universe is essentially a thin gas of black holes drifting in an ocean of cold radiation. You would think they last forever. They don't. In 1974, Stephen Hawking proved that black holes are not perfectly black. At the edge of the event horizon, quantum effects allow particles to escape in a faint, almost unimaginably weak trickle of radiation. A black hole the mass of the sun radiates so feebly that its surface is colder than the cosmic background that surrounds it today, which is why we cannot detect this radiation. It is being drowned out by the warmth of the universe itself. But in the degenerate era, when the universe has cooled below the temperature of even the smallest black hole, the trickle becomes net loss. The black hole begins to evaporate. The numbers are staggering. A black hole with the mass of our sun would take about 10 to the 67th years to evaporate completely through Hawking radiation. A supermassive black hole at the center of a large galaxy, the kind we now image directly with the Event Horizon Telescope, would take 10 to the 100th years. That number, 10 to the 100th, was given its own name long before anyone realized cosmology would need it. A googol. The universe will require a googol years to finish boiling away its largest black holes. Stay with that. By the time you reach that moment, the universe will be older than it is now by a factor so vast that the current age of the cosmos, every star you have ever seen, every life that has ever been lived, is less than a single tick of a clock that has not yet started. And at the end of even that, when the last supermassive black hole flickers out in a final brief burst of high-energy radiation, the universe enters the dark era. There is no good metaphor for the dark era because there is nothing in our experience that resembles it. A sea of photons that will never interact with anything again because there is nothing left to interact with. Stray electrons and positrons, separated by distances so vast that they will never meet. The temperature of this universe is not zero, but it is asymptotically approaching it, falling forever and never arriving. Nothing forms. Nothing changes. Entropy has reached its maximum, and entropy is the measure of how many ways things can be arranged, so maximum entropy means there is no longer a meaningful difference between one arrangement and the next. Time, in any sense we would recognize, has stopped meaning anything. Cause and effect have nothing left to connect. This is the heat death, and this is where the story is supposed to end. Except that Roger Penrose, the British mathematician who shared the 2020 Nobel Prize in Physics for his work proving that black holes are an inevitable prediction of general relativity, looked at the heat death and noticed something that almost no one else had noticed. He noticed that the end looks suspiciously like the beginning. Think about what the dark era actually contains. Massless particles, photons, which travel at the speed of light, possibly gravitons, also massless. Nothing with rest mass survives. And here is the strange thing about a universe of purely massless particles. Massless particles do not experience time the way you do. A photon, in its own reference frame, is emitted and absorbed in the same instant. It does not age. From the photon's perspective, there is no clock. And if you have a universe in which every particle is massless, then there is nothing left in the universe that has a clock either. There is no longer any physical process that can measure duration, because duration is measured by mass. There is also no longer anything that can measure distance. To define a meter, you need a ruler, and a ruler is made of atoms, and there are no atoms. To define a second, you need a clock, and a clock is the oscillation of something, and nothing is oscillating. In the dark era, scale itself becomes meaningless. A universe 10 to the 120th light years across, populated by a few stray photons that will never meet, is mathematically indistinguishable from a universe a billionth of a centimeter across, populated by a few photons in an extremely hot, dense state. There is no measurement that can tell them apart. The geometry has forgotten its own size. And a tiny, hot, dense universe full of high-energy radiation with no rest mass and no preferred scale is exactly what cosmologists believe the Big Bang looked like in its first instant. This is the climax of Penrose's idea, and it is called conformal cyclic cosmology. The endpoint of one universe, stripped of mass, stripped of scale, stripped of any clock that could tell you how long you had been waiting, becomes mathematically identical to the starting point of the next. The heat death is not a wall. It is a door. And the door does not open onto a sequel. There is no sequel, because a sequel implies a memory, and there is no one and nothing to remember. The next universe begins with the same kind of hot, formless radiation our universe began with, and it will run through its own stelliferous era, its own degenerate era, its own black hole era, its own dark era, and at the end of all that it too will hand off to another. Penrose calls each cycle an aeon. Our entire history, every star, every species, every thought ever thought, is one eon, and there is no first aeon, and there is no last. You were promised this would close a loop. Here is where it closes. The question planted at the start of this video was whether the running down of the universe is really a death sentence. And the honest answer, the answer Penrose's mathematics permits, but does not require, is that it might not be. It might be a forgetting. The universe does not die. The universe forgets. Let that sit for a moment, because forgetting is, in some ways, worse than dying. A death has a witness. A forgetting does not. If Penrose is right, then the aeon that came before ours ran for something like 10 to the 100th years. It had its own stars, its own civilizations, possibly, its own physicists, possibly, sitting in their own version of a quiet evening, listening to their own voice tell them about the end of everything. And at the end, when their universe handed itself off to ours, nothing of them came through. Not a name, not a memory, not a single bit of information that could ever, in principle, be recovered. The handoff is total. The amnesia is perfect. This is the weight at the center of this video. We do not live in a universe that is heading toward a clean ending. We live in a universe that is heading toward an ending so complete that even the concept of ending stops applying. And on the other side of that completeness, if Penrose is right, something begins again that has no relationship to us. It is not our descendants. It is not our legacy. It is not us in any sense. It is a fresh universe with a fresh, hot beginning, and the only thing it inherits from us is the shape of its own physics, which, in a universe with no memory, is the same as inheriting nothing at all. And yet you are here, right now, in the inch of the cosmic timeline where things still happen, where the stars are still on, where atoms still hold together, where a brain made of those atoms can listen to a voice and follow an idea across 140 trillion years of future and feel something tighten in its chest. The privilege of being alive in the stelliferous era is not that we get to last. We do not. The privilege is that, for one impossibly thin slice of cosmic time, the universe contains observers. The dark era will not contain observers. The previous eon did, perhaps, but they are gone in a way that goes deeper than death. We are the brief window in which the cosmos can know itself, and the window is closing, and it has been closing since the moment it opened, and there is nothing anyone can do to slow it down. The second law is not negotiable. You are made of atoms that were forged in stars that have already died. The light from those stars is still arriving at telescopes tonight, billions of years after the stars themselves went dark. You are, in a real sense, already a kind of echo. Your body is borrowed light. Your thoughts are the brief organized flicker of matter that will, on a long enough timeline, unravel into photons that will drift forever through a cold and empty cosmos that no longer has any way to measure how long forever has been. And then, perhaps, the geometry will forget. And another eon will begin without you, without any of us, without anything we ever made or loved or said. There is no comfort in this. There is also no horror, because horror requires someone to be horrified, and on the timescales we have just walked through, there is no one. There is only the fact. The universe is running down. The running down is almost certainly its nature, not a flaw. And the running down might, at its absolute end, not stop but quietly hand itself off to a beginning that has never heard of us and never will. The stars you see when you walk outside tonight are not eternal. They are the first sentence of a story whose last sentence is silence, and somewhere on the other side of that silence, the universe is clearing its throat to begin again.